So, in our previous lecture, we went through the derivation of Prandtl's boundary layer theory, and what that gave us was a set of equations for the fluid disturbance field where in the limit of very large Reynolds number, if there is an incident flow, then when we are looking at large Reynolds number defined based on, let's say, an incident velocity u infinity, a characteristic length L, and the kinematic viscosity nu, if we have a very large Reynolds number, then Prandtl's boundary layer equation gives us that in the vicinity of a surface. So, if you have a surface which is in the path of some incident flow, the incident flow need not be a uniform stream, it could also be a non-uniform stream. But what we found out is that Prandtl's boundary layer equation gives us a description of what the flow is in the neighborhood of the surface by having the appropriate, asymptotically appropriate balance of viscous forces and inertial forces. And far away from this boundary layer, we have our Euler's equation or the inviscid description of the flow, where if I write this as the external stream, u du dx is going to be minus 1 by rho dp dx in the external field, and here I have Prandtl's equation giving me the description close to the surface. Now, we also saw different measures of boundary layer thickness in previous lecture. We saw that if I were to actually consider that how to think of the thickness of boundary layer, there are different measures of boundary layer thickness. We saw one based on displacement of streamline, we saw one based on the resisting force that is given by the surface, so that is a momentum thickness, and you could also work out similar measures based on losses of energy, kinetic energy and things of that sort. You can also have an empirical measure by saying that the location where it is around 99% of the incident flow, that is basically my location of boundary layer. Now, as you can see that the equations that you have for Prandtl's boundary layer theory are nonlinear equations. So, the equations that we have here, there is the inertial term, this is nonlinear, which means that you can't really solve these problems for arbitrary cases. So, it is not like you choose an arbitrary u infinity incident flow and you will get a closed form solution. So, there are different problems for which you can get approximate solutions or closed form solutions, but what we will pick up right now is one of the classical extensions or applications of Prandtl's boundary layer equation, which is what is known as zero pressure gradient flat plate boundary layer. So, quite a bit of abbreviation if you want to write down what actually it is. All that it means that you have a flat plate, ideally semi-infinite. Semi-infinite implies that there is an x equals 0 and the plate extends all the way to infinity. And there is an incident uniform flow. So, now we are actually fixing u infinity. So, u infinity is not some arbitrary function of x, but we are saying u infinity is equal to constant. So, there is an incident flow which is u is equal to u infinity x cap, which is incident on the plate at x equals 0. So, because this is a uniform flow that is incident, from our inviscid equation, you can see that the pressure gradient would be 0. Because you have a uniform flow, there is no pressure gradient that is actually there in the inviscid flow. So, dp dx in this problem in the external stream is equal to 0. But then boundary layer equation tells us that inside the boundary layer, dou p dou y is equal to 0, which implies that inside the boundary layer, using the inviscid theory result, dou p dou x would also be 0. So the argument goes this way, that it's an incident flow which is uniform, which means that the pressure gradient in the external flow is 0. The external flow does not have any pressure gradient. The boundary layer equation tells us that the transverse pressure gradient, which is dou p dou y, is equal to 0, which means within the boundary layer there is no variation of pressure in the direction normal to the plate. That means whatever is the value of pressure in the free stream or the external flow is exactly the value of pressure within the boundary layer. This is applicable for any kind of external flow within the Prandtl boundary layer theory assumptions. What we then have, because of uniform flow, because the external flow does not have any pressure gradient, which means the boundary layer will also not have any pressure gradient. Okay, so this is a simplification to our governing equation, which gives us now a reduction to our equation, which is u dou x within the boundary layer, v dou u dou y is equal to nu dou square u dou y square, and obviously you have your equation of continuity dou u dou x and plus dou v dou y is equal to 0. So this is a zero pressure gradient boundary layer equations that we have here for a semi-infinite flat plate. So the flat plate is semi-infinite. What are the boundary conditions? U at y equals 0 for all x is equal to 0. The plate is stationary. V at y equals 0 for all x is equal to 0. There is no penetration on the plate is impermeable. U as y goes to infinity for all x will approach u infinity. These are the boundary conditions that I have. I don't have any boundary condition to prescribe here regarding what is the transverse velocity far away from the plate. So that's something which I cannot fix here. So this is something which we will actually compute or find in the problem. That what should be V? Should this go to 0? What is this quantity? This cannot be given as a boundary condition because then the problem becomes overdetermined. We have a differential equation which is in u, second order in y for the velocity component u. So we have to give two boundary conditions for u. For v, we just have the no penetration boundary condition on the plate. And this is something which we can't specify. It's actually something which will come out of the calculation. We'll eventually find out what this quantity should be. So this is something which is still yet an unknown. Now this problem is what was attempted by Blasius, who was a student of Prandtl. So as part of a PhD thesis, Blasius attempted this particular problem of a flat plate boundary layer with an uniform stream. So it's a very classical problem, both in terms of the theoretical development of boundary layer, in terms of the mathematical methods that are underlying in terms of solving this problem, and also experimental validation. That all that we are saying here, all the theory that is being developed here, how much of these things would compare well with experiments? Because you have to not lose focus of why we are here. We are here primarily from a starting point that there is an inability to compute drag for uniform flow or uniform translation of an object. That is basically our initial motivation. This is how we started things out. We said, how do we compute drag when there is a uniform translation of a body or there is uniform flow past a body? The body is going to resist. What is that amount of resistance that we have? So this is something which we are incapable of finding from inviscid theory. If you did an inviscid flow calculation for this, there is a uniform flow past a flat plate. what would be the velocity field? There will be no change because the fluid can slide happily over the surface. The fluid has no obligation, there is no communication with the fluid. This is the point which I am emphasizing again and again. The communication with the plate is only enabled through viscosity. If there was no viscosity, a uniform stream which is incident on a plate, so if you think of the desk in front of you, if you blow air over that desk, that is like a crude realization of the problem we are doing. The desk is like a flat plate, you are blowing wind over it. So if you just say for the sake of our argument, it's a uniform flow, that's what you are trying to do. Now, if this was a perfectly inviscid problem, the air that you are blowing out, that air would be able to slide nicely over the desk without experiencing any retardation. So, if you place your hand at different points on the desk, you should basically feel the same intensity of that wind. But that's not what happens. If you take a fan and put it over a flat surface and you put your hand at different distances from the fan, the amount of thrust or the amount of wind that you are experiencing just by a feel from your hand is going to keep diminish as you keep further moving down. So, there is a degree of resistance that you are experiencing. Obviously, there is resistance in the bulk, but there is also resistance from the surface. So, this is the problem which takes us through how we understand what's going on and also give us a measure of the drag force that we can calculate. Now, if you look at this equation, and this is a point which we have already discussed earlier, if you just do a quick recall of what we did in the unsteady flow calculation, in the unsteady flow calculation, you solved an equation which was dou u dou t, nu dou square u dou y square, and you had a velocity which was u at y equals 0 for all positive time t was some u infinity, and then u at y goes to infinity for all time was equal to 0. These were your boundary conditions, and you had an initial condition that the fluid velocity was 0 everywhere. Now, obviously, you can do the problem in the reference frame of the plate, in which case there is a uniform stream that is sliding over the plate. We did the problem where the plate was impulsively set into motion. You can do the exact same problem by arguing that the plate is stationary and the fluid is impulsively set into motion, in which case u at y equals 0 for all positive time t would be 0, and u as y goes to infinity for all time t would approach u infinity. This is just a change of reference frame. Now, in that problem, if you remember, how we went about arguing was that this unsteady momentum diffusion problem doesn't have an inherent length or time scale. And because it didn't have an inherent length or time scale, we started by saying, if I were to write this quantity u by u infinity, it's going to be a function of y, t and nu. The left hand side is non-dimensional, which means the right hand side should also be non-dimensional, which gave us this, that f is equal to y by square root nu t. Now, if you look at the two problems, there is some degree of an analogy that is there, the point that we have elaborated before, that the x coordinate, this is my x coordinate and this is y coordinate, my x coordinate which is along the plate is like a proxy for time. It behaves like a temporal coordinate. There is an initial condition, there is in x, and there is a boundary condition in y. What is the initial condition? The initial condition is at x equals 0. What is the incident flow? So, I didn't say anything about initial condition here. There is an initial condition here that u at x equals 0 for all y is u infinity. That's the inlet condition. So, inlet condition is like an initial condition in time. Now, if you want to first argue that how important is the initial condition. In the unsteady problem, we had an impulse. So, there was no time scale that was there in the problem. So, at any time in the future, we had the solution behaving, forgetting what was the initial condition that was there. So you had this diffusion which had a similarity kind of a solution. So here, if I am substantially far away from the inlet, do I have memory? Is there a downstream memory of the inlet? Like, where was the x equals 0 point? Now this is a tricky question because you have a problem here where there is an inlet boundary condition and you are asking how far down in x should I go, after which I don't really have any memory of what was my inlet. This inlet condition kind of becomes unimportant. If you remember, in the unsteady problem, we finally had the 3 boundary condition becoming 2 in the similarity variable. There was just 2 boundary condition. 2 of the boundary conditions collapsed and became 1. So in the flat plate boundary layer, you can solve this problem exactly. Like the equations that you have here, you can go ahead and solve this numerically. This is perfectly fine. You can just crunch it into a computer, solve it marching in x, define what is x equals 0, give an inlet, and then watch what happens. Now if you have gone to the regime where there is a loss of memory of the inlet condition, which means I don't really know what was the inlet condition that I had. So because I have a loss of memory of that inlet condition, if I can go sufficiently further x down in the downstream direction, can I think of this problem just like what I did in the unsteady diffusion problem? So in the unsteady diffusion problem, just the way we did that particular calculation, what if I propose that u by u infinity, I'm just using the same kind of an argument that we used in that particular problem. So I'll say u by u infinity is going to be some function of, here instead of time I have x, and then the other variables remain the same. Now is it possible to do left hand side is dimensionless, right hand side should also be dimensionless. Now is it possible to construct a dimensionless variable using what I have inside the bracket? X, y and the kinematic viscosity. Now x has dimensions of length, y has dimensions of length. Kinematic viscosity has dimensions of length square per unit time. So this has L, this has L, and this has L square T inverse. So whatever you might do, there is no way you can take combination of x, y and the kinematic viscosity and get a non-dimensional variable. It's not possible. There is no way you can construct time using x and y. Which means the argument that we had earlier of saying that u by u infinity is a function of whatever else is left and then going ahead and doing that in a neat manner is not really going to work out so nicely here. And you can see that this argument is bound to fail, because when we argued that u by u infinity had that kind of a, or u depends on u infinity and there was no u infinity, what was the rationale for that? What was the justification for doing that? The equation that you had was linear. Here the equation that you have is non-linear. It is not a linear equation. So u by u infinity is not expected to be independent of u infinity. If you scale this equation, if you divide everything by u infinity, will u infinity will vanish out of the equation? Consider all the velocities that are here. This is kinematic viscosity. All the velocities that are here, if you scale it by u infinity, you will still be left with u infinity in the equation, which is unlike the linear equation where the equation is invariant by this scale factor which is of u infinity. So that means in this particular equation I have to write it in this following manner. F has to be a function of x, y, nu and u infinity. Now you can give it a shot. Is it possible to construct a non-dimensional variable using these combinations? So y obviously has dimensions of length, x has dimensions of length, kinematic viscosity has dimensions of length square per unit time, and u infinity has dimensions of length per unit time. Right? Now, the moment you take nu by u infinity, the dimension of this object is L. The ratio of the kinematic viscosity to the uniform flow is an object that has dimensions of length, which means square root of nu x by u infinity, this has dimensions of L. Nu by u infinity has L, x has L, so that is square root of L square. So then I can now say that there is a length scale in the problem, which if I write as square root nu x by u infinity, which can be used in order to non-dimensionalize my problem. So based on dimensional argument, I can now say, yes, I can write a non-dimensional equation scaled by u infinity in terms of a variable that is y by a length scale, which scales as square root nu x by u infinity. It is similar to square root nu t that we saw earlier. In terms of how diffusion, we are trying to draw this analogy between time and the streamwise coordinate. So there it was square root nu t. So here similarly there is a square root nu x, but based on dimensional argument it has to be square root nu x by u infinity. So you will expect your solution to take this particular form, where delta x should be something like this. So now we will do this formally. So what we are going to now say that there is a lack of length scale in x and y. Earlier we said in our unsteady diffusion problem that there was no length scale, which was actually only in y, and there was no time scale. Now we are going to say there is no length scale in x, there is no length scale in y. Because there is no length scale in x and y, we are going to seek solutions which are going to be of a similarity form. The governing partial differential equation that we have, which is Prandtl's boundary layer equation, we are going to seek solutions for this equation by arguing that there is no inherent length scale either in x and y. So that is the justification. So you use the dimensional argument to actually say that solution should take this particular form, and now we will formally get what delta of x is. So our starting point is the following. We will define a similarity variable which is y by delta of x. At this moment I don't know what delta of x is. We have obviously got a clue based on dimensional argument, but we will get this in a more exact manner. So we will say that there is a similarity variable here where the transverse coordinate y is scaled by some thickness which is x dependent, and this automatically tries to give you a feel that what is it that you are doing? What you are doing is you are stretching the boundary layer. See, the whole idea of boundary layer theory is that there is a very thin region close to a surface where viscous effects are important. Now, if you want to study this problem where you want to look at the problem at the scale of boundary layer, it's like taking a magnifying glass which only zooms in one direction. It doesn't zoom in the flow direction, it only does a zoom along the y direction. So, this is that zooming factor. That is what you are doing. You are basically saying that the actual value of y, where you are looking at it, on scales of x is going to be very small. If you say that I have travelled a distance, let's say capital L along x, the equivalent distance which you would be actually looking at in y would be very small compared to L. That's the fundamental philosophy of boundary layer. So, in order to look at them in a similar zoomed in version, you don't do a zooming which is equal, you do an unequal zooming. You are doing a zooming in the boundary layer coordinate by saying that let's define a new coordinate where the vertical coordinate, the transverse coordinate y is blown up. So, instead of looking at a coordinate y, we are going to look at in a coordinate which is y by delta of x. And delta of x automatically now starts giving you a clue. It's like some measure of your boundary layer thickness. It's some ways of thinking in terms of your boundary layer. So, if you are at the edge of boundary layer, the quantity eta is basically going to be order 1 or large, whereas the actual value of y might be very small. This is the basic idea, because once you get this clear, after that what follows is more of routine algebraic calculation. So, with this we will proceed. So, we have now the idea that u is u infinity some function of eta. Now, what we will do here is, okay, let's for the sake of keeping the variable consistent with what we will introduce later, I will just call this variable as g instead of f. It's just to keep it familiar to how the boundary layer equations will work out. So, you will have small u is u infinity g of eta, where eta is some y of delta by x. This delta of x right now is unknown. You have a clue. You already know from a dimensional argument what delta of x should be, but keeping that, and we will come back to this clue later, but right now we do not know what delta of x is. It is something that depends on all the variables. Now, unlike the unsteady diffusion equation, where there was only one dependent variable, which was the velocity component u, here you have two dependent variables, u and v. So, instead of working with two dependent variables, what we will do is we will introduce the stream function. This is a two-dimensional incompressible flow. So, I am going to introduce stream function where u is dou psi dou y and v is minus dou psi dou x. Now, given this particular definition of u, I can try computing what is psi. So, psi is going to be an integral 0 to y u dy. Now, is this entirely correct? Psi is equal to 0 to y u dy. Ideally, psi should be integral 0 to y u dy plus some function of x. That is how we learnt about stream function. Now, why am I ignoring that function of x? I am ignoring that function of x because psi at y equals 0 is going to be k of x. And what is psi at y equals 0? That is the value of the stream function at the surface. And the value of the stream function at the surface should be 0. It should ideally be a constant. You can choose whatever constant you want, it will be 0. So, that is the reason why that k of x is not there. The surface is also a streamline. So, it is a surface of constant stream function. So, psi is equal to 0 to y u dy, and I am going to now substitute. So, instead of y, I can write this now as delta of x 0 to eta u d eta, and then if I substitute for u, I will have u infinity integral 0 to eta g eta d eta. So, this is what I am assuming regarding the form of the streamwise velocity u, and so this is what I will have for the stream function. So, now I am going to define a variable f of eta such that g of eta is d eta of f of eta. What that does, that helps me write my stream function. Instead of an integral, I am writing it as a function of eta, that is all. So, this is an integral of g of eta from 0 to eta. Instead of that, I am writing it as f of eta. So, which means that your u would be u infinity f prime of eta, right. What should be v? V is minus dou psi dou x. Minus dou psi dou x can be written as minus dou x of psi, which is delta of x u infinity f of eta, which I can write as minus u infinity delta prime of x f of eta, and then I will have plus delta of x d eta dx, which would be y by minus delta x whole square delta prime of x into f dash of eta. So, you take the x derivative. When you take the x derivative of f of eta, so when you are writing dou x of f of eta, that would be df d eta multiplied by dou x of eta, which would be y minus delta square d delta dx. Okay. So, that is basically your expression what you have for your the velocity component. So, we will require them later. So, this is 1 and v is going to be minus u infinity delta prime of x with a minus sign f of eta minus y by delta is going to be eta. So, eta f prime of eta. So, v is u infinity delta prime of x eta f prime minus f. So, we will require these later because now we will write the equations in terms of f and then compute u and v. Okay. So, now let us go to our equations. U dou x plus v dou y is equal to nu dou square u dou y square. Continuity is already satisfied when we use the stream function. So, now I am going to use u as dou psi dou y and v as minus dou psi dou x. Let us substitute. So, the first term is dou psi dou y, the second term is dou square psi dou x dou y. V is minus dou psi dou x, and dou u dou y will be dou square psi dou y square, and the last term is dou cube psi dou y cube. So this is basically the equation that you have for your Prandtl's boundary layer equation when I use the stream function formulation. I don't need to use continuity because that is automatically satisfied with the formulation of stream function. Okay. Now I need boundary conditions. Boundary conditions in terms of stream function. Now one boundary condition was u is equal to 0 at the plate, u is equal to u infinity far away, which means dou psi dou y is equal to 0 at y equals 0 for all positive x, because this is a semi-infinite plate, and dou psi dou y will approach u infinity as y by delta goes to infinity. So I am looking at the variable y by delta going to infinity, because y is not necessarily, y equal to infinity lies in the free stream, right? The actual y equal to infinity is lying in the free stream. Now in this problem, u infinity doesn't change because it's a uniform flow, so it doesn't matter. Y being equal to approaching infinity and y by delta approaching infinity will give you the same thing. But in other problems where you have the inviscid exterior, the y approaching infinity is inaccessible from the boundary layer. The boundary layer cannot access infinite distance from the plate because that lies in the inviscid region. It can only access the edge of the boundary layer, which is y by delta going to infinity. Any other boundary condition? Obviously psi is equal to 0 at y equals 0 for x greater than 0. That's the fact that the plate is a streamline. Okay. So now let's try to write these equations in terms of the formulation, which is psi is equal to delta x u infinity f of eta. So now I have psi is equal to delta x u infinity f of eta, where eta is y by delta of x. Let's substitute. So let's do one at a time. Dou psi dou x. What will be dou psi dou x? We have just calculated what is dou psi dou x when we had to find v. So it would be u d delta dx f minus eta f prime. V is minus dou psi dou x, which is what we had here. So right now I am writing dou psi dou x here. Okay, so that's one term. Dou psi dou y. What is dou psi dou y? Dou psi dou y is easy because I have delta x here. So that is just going to be u infinity delta of x f dash of eta and then d eta dy, which is 1 by delta x. So it is u infinity f dash of eta. So these are all functions of eta. Okay, now let's do other terms. Dou square psi dou y square. We have dou psi dou y done, dou psi dou x done, dou square psi dou y square. Let's do that. So that's going to be taking a derivative once more. So it will be u infinity f double dash of eta, then d eta dy, which is 1 by delta. And we have dou cube psi dou y cube, which would continue in the same manner, and you are going to get dou square here. Now the slightly complicated term is that mixed derivative, which is dou square psi dou x dou y. So I have already done dou square dou psi dou x. So this is dou y of u infinity d delta dx f of eta minus eta f dash of eta. Now u infinity is independent of y, delta is independent of y. So I have dou y of this term in the bracket, which would be f dash eta minus f dash eta minus eta f double dash eta, and then d eta dx, which is 1 by delta. Right? I will have an f dash from this term. Then when I take a derivative with respect to eta, that will also give me an f dash. So f dash, and then minus eta f double dash. So this turns out to be minus u infinity d delta dx 1 by delta eta f double dash of eta. So we have all the terms that we need, and now we can substitute. So we can plug in all the terms in the equation. So for dou psi dou y, it's going to be u infinity f prime or f dash, and then for the mixed derivative it will be minus u infinity d delta dx into 1 by delta eta f double dash. Then for dou psi dou x, it's u infinity d delta dx into f minus eta f dash, and then the second derivative, which is u infinity f double dash by delta, and the right hand side is the third derivative with respect to y. So that is u infinity f triple dash by delta square. Now if you look at your equations and divide throughout by u infinity square by delta. So I have u infinity square by delta throughout with that minus sign. So I am going to divide the entire equation, divide by minus u infinity square by delta. Then I will get f dash d delta dx eta f double dash plus f minus eta f dash f double dash is equal to minus delta by u infinity square, u infinity by delta square with a kinematic viscosity nu f triple dash. There is also a d delta dx here. Now if you look at the two terms here, f prime or f dash eta f double dash, there is also a minus f dash f double dash here. So they will cancel. This term and this term, they are going to cancel each other. Right? So finally, what you get is f double dash d delta dx is equal to minus u infinity nu u infinity delta f triple dash. So what is my final equation? My final equation is f triple dash of eta is equal to minus u infinity delta by nu d delta dx multiplying f of eta, f double dash of eta. Now, if this was truly a similarity solution, then what should happen? If everything here was truly a similarity solution is what I am looking for, that there is a variable eta which is y by delta of x, if that's indeed what should happen, then this coefficient should be independent of x, because you look at the left hand side. The left hand side is purely a function of eta. It's neither a function of y explicitly or x explicitly, it's only a function of eta, which means the right hand side should also be purely a function of eta, not an explicit function of y or x. So, if this is also a function of eta, that leaves me with this quantity which is only a function of x. This is a function of x, this is not a function of y. So, the only function of x that is permissible is a constant. It can only be a constant. Now, what do you choose as a constant? Now, this obviously you have a choice. What do you want it the constant to be? Because finally that will get reflected in the equation that you have. So, your f will accordingly change. Like if you choose the constant to be 1, accordingly you will solve one particular differential equation for f. If you choose the constant to be something else, the equation will correspondingly change. So, for the ease of your calculation, one choice of constant is to have this be half. Again, there is nothing sacrosanct about this value of constant, because it will adjust in terms of what will be the equation for f, and accordingly f will get modified. So, if you choose this f to be half, what you have here is d delta dx is equal to half or nu by 2 u infinity into 1 by delta, or rather I can keep the delta here. I'll keep it here. So, 2 delta d delta dx is equal to nu by u infinity. Now, this is where you will see it becomes convenient, because now I can write this as d of delta square is equal to nu u infinity dx. So, the reason I chose that factor of half is to remove the constant value from here, so that I can just write it as a total differential of delta square. So, if you integrate this equation, you will have delta square of x is equal to some constant plus nu by u infinity of x. Now, what is the choice of that constant? Now, this basically says what is the thickness of that boundary layer when it starts at x equals 0. So, if we say that the boundary layer is starting at x equals 0, I can equate this to 0, that constant. So, I have then delta of x is equal to square root nu x by u infinity. So, if you go back to the beginning of today's lecture, what we arrived at from dimensional arguments, right now we are getting it from a formal analysis. Then the numerical factor, by the choice how we have made it, that numerical factor is also unity. So, we had already preempted this, we had already guessed this from the dimensional argument, now we have it from a formal analysis. So, this quantity is square root nu x by u infinity. So, and going back to our equation for the boundary layer variable is going to be minus, so I can bring it to this side, f of eta, f double dash of eta is equal to 0. So, this equation is known as, so I have chosen it to be half, sorry. So, this is half. So, this equation is known as the Blasius equation. And you can probably recognize the tremendous simplification that has happened to the system. You started out with a nonlinear partial differential equation in 2 variables, and you have reduced this to an ordinary differential equation in a single variable, which gives me my stream function and thus the velocity components. So if you are able to solve f, now you obviously need to know the boundary condition. Now what are the boundary condition? The boundary condition was, if you go back, you had your boundary condition as u, or in terms of psi, we had a boundary condition which was dou psi dou y is equal to 0 at y equals 0. Now y equals 0 means eta equals 0, and dou psi dou y would imply, so if psi is delta of x u infinity f of eta, and if I am saying that dou psi dou y, then dou psi dou y we have already computed to be u infinity f dash of eta, which means at the plate y equals 0, it implies eta is equal to 0. F dash of 0 is equal to 0. At the edge of the boundary layer, where y by delta approaches infinity, this implies eta approaches infinity. So your boundary condition is f dash of eta equals to 1. Right? Because dou psi dou y approaches u infinity, which means f dash of eta should approach 1. What is the other boundary condition at the plate? Psi is equal to 0, which means f of 0 is equal to 0. You have obtained a third order differential equation. So you need 3 boundary conditions. So the boundary conditions are f of 0, f dash of 0 are 0, and f dash of infinity is equal to 1. And you know where they came from. F of 0 came from no penetration at the plate, f dash of 0 came from no slip at the plate, f dash of infinity came from matching with the free stream solution. Now this differential equation, the Blasius equation, even though this is an equation which is an ordinary differential equation, it's still nonlinear. You have done a significant simplification to your system, but it is a nonlinear equation. And by virtue of being a nonlinear equation, you can only solve this equation numerically. So you have to solve this equation using various numerical techniques. So this is a boundary value problem. There are various boundary value solving techniques that are there numerically how you solve it. You give a value at eta equals to 0 for the function for its slope, and you also give a value of its slope at infinity and you find the numerical solution. The other way to find the solution is you solve it approximately. Approximately means when eta is very small, and the other being when eta is very large. Because when eta is very large, we know that f dash of eta, as eta tends to infinity, this is going to go to 1. So you can get some approximate solution. So I'll directly move on to what the profile will look like. So if you plot u by u infinity as a function of eta. Now what is u by u infinity? F dash of eta, right? U by u infinity is actually f dash of eta. This is what it would look like. As you go further away from the surface, so eta equals to 0 is the plate. Eta approaching infinity is approaching the free stream region or the inviscid region, and it will approach 1. So this is what you will get for your tangential velocity. Now what about your vertical velocity? V by u infinity. Now the vertical velocity, if you go back, you see is eta by eta into f dash minus f. Now f dash goes to unity. F should then go to, so for large distance, f dash of eta is approaching 1, and then there is a correction to this, a correction which actually goes to 0 as eta goes to infinity, because f dash is going to approach 1 asymptotically with some term that vanishes as eta becomes large enough. So which means f of eta for large values of eta will go as eta. Okay, so f goes to eta, and that will actually give us what would be our vertical velocity. So vertical velocity, if you compute, v will be in terms of delta prime of x, so that is nu u x eta f dash minus f. So if you write v by u infinity, that would be 1 by 2 Reynolds based on x eta f prime minus x, where Reynolds based on x is u infinity x by nu. It's a Reynolds number based on your streamwise coordinate. Now if you substitute the values of f prime and f into this particular expression, you will find that this turns out to be a constant. So it is 4.9, sorry. So it turns out to be a constant which is 0.86 by Rex. So the transverse velocity that you would actually get, so here if I write v in scaled with that factor of Rex, I will find that the vertical velocity at the edge of the boundary layer doesn't go to 0, but rather it is achieving a constant value. So there is a net non-zero vertical velocity or transverse velocity at the edge of the boundary layer from the Blasius solution. So we'll stop here. We still need to discuss a little bit more with Blasius solutions regarding what would be the boundary layer thickness, and most importantly, the whole reason for doing all of this is to compute the drag force on the plate. So that's what we will do in the next lecture. Thank you.